Welcome back. Today we're going to build the memorizing part of memorizing transformers, finally. So, if you remember from our paper, section 3.1 talks about the KNN augmented attention layer. And this is really the crux of the paper. This is the idea that we're testing. So, as a refresher, say we have a 12-layer model. 11 of these layers will just be doing regular self-attention. The layer that is second from the top will be doing KNN augmented attention. And so in this transformer block, there's two branches of computation. One of the branches is regular self-attention. The other one is pulling out key value projections from past runs of data and using those for self-attention. So instead of using the key value projections from our current input, we actually look over the key value projections from all past inputs, and we find the ones that are most similar, and then we perform attention with those. So one branch is doing local current time step self-attention with the key values from the current time step, and the memory one is using past key value projections. And then we combine these and pass it into the last layer of the model. And this combination is gated, so this is a learned parameter per head, but basically we're just saying G will be a number between 1 and 0, and we're just weighting these two to say how much do you want of the memory and how much do you want of the local context at each step. So that's kind of the main idea, and pretty much everything is contained in here. And there's a note about distributional shift, or kind of the drifting of these projections, but we'll look at that as we build. So I've pulled out all of the relevant kind of text here just so we have it as a reference and we can come back to it, but now we can start building. So I've started by importing our basic libraries here. So what is the first thing we need? And the hint here is that I've imported faiss. So faiss is a library from Facebook that came out quite a few years ago, actually, 6 or more. It's a library for efficient similarity search and clustering of dense vectors. I like faiss because it's been around a while, it's very well documented, it's very robust, it's very fast, but really you can use whatever you want. And in particular in the last couple of years, there's been kind of an explosion of vector database products. So use whatever you're comfortable with, whatever you want to use. It doesn't matter too much, we just want to support the basic operations. So the interface will just be adding, searching, and some kind of removal of vectors from a database. So let's get started with faiss, and I'll give you a quick example to see how it works. So the main object in faiss is called an index. And this is basically their vocabulary term for the object that will hold all of our vectors that we will search against, that we'll add new vectors into, that we can remove from. So the index is the core object in faiss. And we have to initialize it with some kind of dimensionality. So here I'm using index flat L2. And there are a lot of different kinds of indexes here. And so we're going to use something very simple. Index flat L2 means L2 is the distance metric, so this is Euclidean distance. It's going to be exact and brute force. And we're going to store flat. And this is opposed to all of these other different ways of storing your vectors. So there's quantization options. I'm not exactly sure what some of these are, but the idea is you can trade off speed, accuracy, and memory footprint. So this, for example, I believe partitions the index space so that instead of searching the entire index, you actually have some idea of which neighborhood you're going to look at. You search that, and it gives you, with certain accuracy, the answers that you want. But really the idea is, you can read into these, the idea is that you trade off speed, accuracy, memory. So for our very simple case, we'll use index flat L2. One more note is that you have to be a little careful because these different indexes support different operations. So for some of them, you'll be able to add and remove vectors arbitrarily. For some, you won't. For some, you will have to actually train them because it's essentially creating a graph. Each time you add new vectors, it needs to add these into its graph so that it knows where to look for new vectors. So just be aware that the interface changes depending on which index you use, and some operations are and are not supported. And so I've written a maybe too exhaustive set of things to think about when you choose this, and Facebook does, in the library, a very good job of answering some of these questions, but I've put this in the notebook, and it's just a few things to think about. What are the required operations? Are we going to have to remove? Are we going to have to reconstruct, search? How often are we going to have to do each of these? And for the given index, how fast is each operation? So there are different operations here and different things to consider given the speed of each and how often we'll need to use each. This is also in tandem with your accuracy, speed, and memory footprint requirements, the size of the index, the size of the query, what hardware you want to run this on. Another special consideration is that for some of the indexes, each time you add, you have to retrain the graph. So you can't arbitrarily just keep adding and querying. So this applies beyond faiss. It should apply to anything where you can really fine-tune the details of your vector search database product. So we've got our index initialized. Let's add some data. So we've just created a NumPy array, and this is 10,000 vectors of our specified dimension, and these are just random float vectors. We add them to our index with index add. And now if we look at our index, we can see we have 10,000 vectors stored in here. This index also supports removal, so if we want, we can remove the first 10. And now we can see, okay, we've removed 10. So now we have 9,990. It's just a very basic overview of how to use faiss. And now the important part, let's get some query data. And so this supports batch querying. So instead of just searching one vector at a time, we have a batch of vectors. Specifically, we have 10 query vectors, and we want to search our index. And let's say we want to get the two nearest neighbors, the two most similar, according to Euclidean distance, and we want to return those. And the interface here is that when you search, you get both the distances and the IDs. So the distance is how far the two closest neighbors were, and the IDs are the indices of these neighbors inside of the index. So for our first random vector that we're querying against our database, vector 9,238 was the closest, this one was the second closest, and these were the associated distances. There are a few more operations that are particularly relevant. So this is something we can also do, which is search and reconstruct. So you'll notice here we only get the distance and the ID, but we don't get the actual vector that we put in to begin with. And so we're actually interested in recovering the vector. So search and reconstruct will give us the distances, the indices, as well as the original vectors. So if these are our key value vectors, we've added them into our index. We're searching with our query vectors at some point, and we recover the distances, the IDs, and the actual vectors. So it's a very handy method. There's one problem in that we're sending our key value vectors into the database, but we only actually want to search the keys. We're going to be putting our keys into the faiss index, but then we want to search over that, but then we want to get the keys and the value vectors back. So what we actually need to do is we create an index with faiss, and we put all the key vectors in there, and we search against that with our queries. But we need a separate place to store the key value pairs for each token. So we're going to be building two things simultaneously. One is a faiss index, and one is some other kind of database where we hold on to our key vectors. So we search the index, get the IDs of the vectors we want, retrieve them from our database, and send them back to our model. All right, let's add a database. Here, we'll just use a NumPy array because it's very simple and it's going to be very fast. But specifically, we want to use a memory mapped file. A memory map file is just a file, but instead of the expensive read-write you have going to disk, so it takes a long time to get your data to and from disk to the CPU, or the GPU, as we'll talk about later. Memory mapping brings the file into your memory so that those read-write operations are much, much faster. So we'll create a memmap NumPy object. And for our purposes, the really nice thing is that this has the exact same interface as just a NumPy array that sits in memory. So you won't have to do too much relearning here. So we'll call our database memmap mode. This is how we interact with it, so it could be read-only, write-only. This should be very familiar if you work in Python. And now we have shape, which is required here. So what actually is our shape required? Well, let's see. We're taking the key value vectors out of the model, and we need to stick them into this memory. So the shape will need to be whatever our max memories are. So this will just be the ultimate size of the database. And then we want 2 as the dimension here, because we'll have key value pairs, and then whatever the dimension is that we've got. So this will be our shape, and let's define max memories to be 10,000 here. Okay. This is initialized with zeros, and if we insert some random data here, we can see, oops, we're using the wrong dimension. We've just added to our memmap file, to our NumPy array. So that's the basic interface of these two objects we'll be working with, and we'll use these to construct a search for KNN, store, and retrieval for our key value vectors. Okay, so we've introduced the main tools that we'll be using to create our KNN search and the storage of our vectors. So I've summarized what we've talked about here, and here we're initializing an index, initializing a database, and we have some configuration parameters up here. So now let's think about what we need to build. So we'll need some kind of KNN database class that our model will talk to in order to send and retrieve vectors. And this class will need to do a few things. So we'll need to add to the index, add to database, query the index, and then given the results of that query, we need to retrieve from the database. And then we'll need some way to remove or clear from both the index and the database so that we can make room for new memories. Okay, so let's start with the adding functionality. The first thing we should do is get some fake data, or real data if you like, but we'll use fake data that is in the right size so we can figure out what shape the data will take as it goes through our database class. Let's remember back in our decoder blocks, our key projections were this size: batch size by sequence length by dimension. And so when we're passing this from the model into this database class, we're actually going to be stacking the key and value projection together and sending them through since it's more efficient. So we're going to stack these, and it'll look something like this. So we'll receive as input a key value vector, and it'll be in this shape. Let's think a little bit about what we want to do with this data. So what will we actually be putting into both the index and the database? Well, this is of shape batch times sequence length times 2 times HD, where HD here is the number of heads and the head dimension size. But we can just think of it as it'll be one dimension. So what do we actually need to put into our database and our index? Well, let's say we have a batch of 16 and the sequence length is 512. We want to simply, because we're looking by token, we're just going to store 8,192 vector pairs. And similarly, so that's the vector pairs will go into the database. And into the index, we'll just have 8,192 HD dimensional vectors. So let's see what that looks like. The first thing we need to do is reshape this. So we just want to combine the batch and the sequence length dimension such that our first dimension will just be individual tokens instead of batch by token. And this tells it infer the first dimension, and we're going to keep 2 and dim as the last dimensions. So these first 2 dimensions will be combined here. So we have 8,192 pairs of key value projections here. Okay, so that's what will go into the database. And then remember that for the index, we're going to query not the key values, but just the keys. So we actually need to separate this out further. So we just want to grab the keys, and that can be done just by indexing. So we'll assume that the order is key, then value. And so we're grabbing the keys. If we wanted to grab the values, we would put a 1 there. Oops. Great, and so this is what we'll add into the faiss index. We'll get the results, and we'll come into this, and we'll grab our key value vectors and send them back to the model. So let's go ahead and add the keys to the index. So we run into an error here, that the array is not C-contiguous. Contiguous and non-contiguous just refers to the fact that a contiguous array has all of the memory blocks next to one another. And non-contiguous has it separated in some way that faiss doesn't like. And so this is an important concept, and you'll certainly run into it when you use view, reshape, transpose, any kind of dimensional modifications on arrays. And so because we've used reshape, the memory is no longer contiguous. So it's moved around, and faiss doesn't accept this. The fix for this is that we call as contiguous array, and then it works. So this, I'm fairly sure, just creates a copy of the data as a contiguous array, and this is what we pass into faiss. So sometimes you'll need to call this function, and this is the fastest way to do that. Okay, so we've added to our index. Now let's add to the database. So if you remember here, when we add, this just acts like a NumPy array. So it works by indice. When we add to the faiss index, it just stacks new data on top of old data. So it's continually just adding, and we don't have to keep track of any index. But here, for the database, we want to keep track of where we are. If we kept adding in the same position, it would just be overwriting our old data over and over again. So we just need to be careful here. What we can do is create just some offset value that tells us where we are as we keep adding data. Let's define the kv length as basically the number of vectors that we're going to be adding here, or rather the number of vector pairs, because it's kvs. And then instead of just adding the IDs as the KV length, we'll add this dB offset value, and then dB offset will just increase by KV length. And so every time we call this, we'll hold on to this value. We won't reinitialize it as 0 every time. And this way, every time we add, we'll know that the IDs will be in the correct place. So we'll be putting the values in the correct place. So there we go. We've added to the index and the database. Okay, so we've finished adding in our data to the index and the database. So let's move on to the next piece of functionality for our database class, which is to query the index, and we'll combine this with retrieving the results of that query from the database. So let's think about what is the query data that we're sending from the model into this database class. Well, it will look something like the key data we just looked at. So it will be a query projection that is batch size by 512 by dimension. So let's create some fake data that we can query our old key values against. Remember that this is a batch by sequence length by dimension. But just like we did with the keys and the key values, we want to flatten this. So let's do that again, and we can just reshape it. And then -1 just tells NumPy to infer what should this shape be. So this is good. We've flattened out the batch and the sequence length dimension. Well, now we have 8,192 tokens in our query projection that are 10 dimension long. So let's search our index with these query projections. So I've already defined top K up here. And this is just saying for each query, I want you to look at all the past key values and find the top K most similar. So let's find the top 3 most similar vectors to each of our query vectors. And if you remember for this search function, the results we get are distance and the indices, but I'll call them IDs so that we don't confuse this with index, indice. So, great. We've run our 8,192 queries, and we've gotten the 3 most similar vectors for each of these 8,192 vectors. If we take a look at that, our first query vector, the 3 most similar are ID 2036, then 2563, and so on. So this is showing us the 3 most similar. Okay, now we have the indices. We know where the key value pairs are. Now we need to go fetch them, because remember, this is just finding the most similar key vectors. We want to get the key value pair. So for that, we need to go into our database. And we can just do this by indexing straight into our database. So we get out of this 8,192 results that we have the 3 most similar KV pairs, which are 10 dimension long. And so we're not quite done. If you think about what our model is passing in and out, the final result that we want to send back to the model is we need to unwind this dimension. Remember, we collapsed the batch and the sequence length. So we need to split that out again. So let's do that. So we want to turn this 8,192 into 16 batches of 512. 3, 2, 10. Those stay the same. Okay, and this is what we'll send back to our model. So we set the queries in, and what we got out is, for these 16 by 512 by 10 queries, we got 16 batches of 512 token lengths of the three most similar KV projection matrices that were the most similar to our queries. And so this is what we'll use to perform the memory augmented self-attention. So we've completed the add, the query, and the retrieval function. And so this is what's being passed into and out of our model. Okay, it's time to look at removal, clearing, database management in general. So as we keep passing data through the model, it's going to keep sending our key value projections into the database and into the index. And we don't want to do that indefinitely. This will just grow and grow and grow. Searching will become slower. We'll run out of memory. So in the paper's approach, they use a separate memory for each batch dimension. So what we've just built, if our batch dimension is 16, we would just have 16 separate memories. And each of these is responsible for handling the same document that, remember, is fed through the same batch dimension. So one long document gets split into chunks, and it's assured that each of these chunks will follow in succession, and they'll be in the same batch dimension. And we also have to deal with variable length documents here, because some will be shorter, some will be longer. So we'll have to make sure that these are clearing at the right time. And they won't always, of course, match up with our discrete chunk size, so we'll have to do some padding or find another way to manage this. So I've thought about this a little, and we're going to take the easy way out for now. So we're going to make two simplifying assumptions that should make our code much more legible in the short term, and it will make it functional, and later we can work on optimization, so making the index faster and making it more realistic, as in taking on variable length documents. So we've made two simplifying assumptions here. The first is that instead of having a separate memory for each batch dimension, we're just going to have one. And so every document will go into the same database, and hopefully the model can still learn. The idea behind that is that, well, we're feeding in these different documents, and these will be quite different. They might be scientific papers on very different topics, but the most similar projections, if this is working correctly, should be pulled out of a previous chunk of the same paper and not a previous chunk of some other paper. So we're going to have one memory. That'll make things a little easier. And the second assumption that we're doing is, if you remember when we created the data set, we actually don't have variable length data. We took a bunch of long papers and we chopped them into 5,120 token length sequences. And we said, we're just going to make 10 segments. We're going to call each of these one long document. And we're going to make 10 segments of 512 tokens. And we're going to feed these all through. And the nice thing about this is that these will all match up precisely. And once we're done with 10 passes, we can flush the database and start over again. So we won't really need to do much memory management. It'll be very simple. And once we start running the model and examining how this layer is doing, we can come back and start optimizing for speed, because this will be the slowest part of the model. And we can start adapting it for variable length documents, which is a much more realistic application. So that's kind of the thing we're going to do to make our lives easier here. There's one more thing we have to remember, which will count no matter what scheme we use, is that if we're on the first segment of a document and there are no previous key value projections to look for, we don't want to have our query projection hitting an empty database. So we do need to add some logic that will tell us nothing's been added yet, don't bother going to the database and searching, you're at the first segment, so just pass over this for now. So we'll add that logic into our KNN memory layer. But otherwise, the removal, clear, database management will simply be each pass of 10 segments of 512 tokens, start over again. So very simple, and I hope this will make it much more legible, and we can make it more complex as we go, as needed. All right, I've created a KNN class, and this encapsulates everything we've just talked about. So we initialize the database, we initialize an index, we have an add to database function, search and retrieve, add, search, and something I've added here is clear, so that when we're done with our index and our database, we can call clear, and this will empty out the index and empty out the database, and we can start again with a new batch. So let's test to see if this works. Let's initialize some parameters here. So we're just going to kind of use the same numbers we've been working with, and we'll create some fake data just to make sure everything is working as we expect. So I've got some key value data that we're going to add in, and some query data that we're going to use to retrieve the top k key value pairs. So let's add the KV data, and then great. Inside of our index, we can see that there's 8,192 examples here. And that is the same as our batch size times our sequence length, so 16 times 512. We can look into the database to make sure this is working. So we have a value at the 8,191 index spot, and then from 8,192 onwards, it's all zeros. So that's great, that's what we want. We can even add this in again. Okay, so we've added 2 batches of the same data just to see that it works sequentially. All right, let's search. So we've just called this method search, and this is the main one that you'll call, and this also hits search and retrieve. And a lot of this is, as we saw before, this is just reshaping our data into the correct kind of places. But really, we just have a search and an add function, and it does pretty much exactly what you'd expect. So KNN search, we're going to add in our query, and we need a top k. So we'll get the 3 top results, and we'll call this retrieved KVs. And there we go. So we added some KV data in, we used a query to find the most similar results inside of it. We were able to pull those out. And so this is what we'll be using in our attention. 16 batches, 512 sequence length, the 3 most similar KV couples of 10 dimension. All right, we have our KNN built. Let's wrap it into our multi-head attention class so that we can build a KNN layer. So if we remember, this is going to look a lot like the multi-head attention block that we built a few videos ago, which I'll paste in here. So this should all look familiar. And now we have this to-do portion here, and that is to add in the KNN memory. So we have one branch of computation that's doing local attention, and then we're going to have the memory attention, and then we're going to fuse them here. So let's think about what we need to do. Calling the KNN and searching it is fairly easy, as we've just seen. Add and search, it's 2 lines of code, it's very simple. However, there's a lot of pre and post processing that we have to do to get our query in the right shape, to make sure that we send our KV values in the right shape, and once we get the KV values from memory, we have to reshape them a bunch in order to get our KNN memory working right. So just to kind of get us started, I've written out sort of in pseudocode what our plan would be. So make sure that query is in the right shape, and then we get the KNN values. This is batch by sequence length by k by 2, the coupled KV pairs, and then head times head dimension. And then we have to do a lot of stuff. So we have to like split these apart into the key and value, and we need to reshape them, transpose them. We have a lot of operations to do. It's fairly tedious, and it's also very complex because we want to keep track of our shape at every point, And it gets very hard when we have a lot of transposes and reshaping. And so we'll either have to comment all of these lines of code very explicitly, or as we read through and say we need to make some change upstream, we need to rewrite everything downstream, we just have to go through line by line and think, okay, this dimension moved here. Okay, now I've split this dimension and I reshaped that one. Okay, so it's just it's very kind of unnecessarily complex. So is there a better way to do this? Yes, I only bring this up because thankfully there is. So to help motivate this, let's look at our previous attention scores that we computed up here. So we'll look at how we did it previously, and I'll just create some kind of fake data for us to look at. So we have queries and keys in this shape. They're both the same shape here. What we did, and this is just copying what we've done before, it's splitting out line by line, saying these are all the things we did to get them into the right shape so that we could compute the attention scores. So we have some reshapes and transposes. Now I'm going to show you the einsum einops version. Einops is a library that contains the function einsum, which is in a lot of other libraries, and it contains some other useful functions like rearrange. So we'll look at einsum and rearrange for now. Now let's do the same thing, but with einsum. So fake data here, queries and keys, and this is the einsum example. It's the same computation, but we're using this very specific syntax from these einops operations. So what is this library? There's a lot of tutorials on einops, but more specifically on einsum, because this is implemented in pretty much every major deep learning matrix library. They all have an version of einsum. So there's lots of tutorials, there's lots of videos, and I don't want to turn this into an einops tutorial because it takes a little while to sit with and to practice. So I'll just give you kind of a taste, and hopefully this motivates you to learn it because it's an incredibly useful and powerful tool, and it will make reading and rewriting and writing your code much, much simpler. There's even, and a good way to get started is to take a look at PyTorch examples here. And this just does a side-by-side, just as we've done, of how do you do this manually using PyTorch, and how can you do the same computation using einsum. And so when you compare them, you'll see that a lot of these operations where you're moving around tensors and you're transposing can be really consolidated into just a few lines. Channel shuffle, for example, can be converted into one line, where we have to do a lot of unbinding and binding dimensions. They even have an example of self-attention here. So you can see you can get a version of self-attention that is much more concise. And once you learn to read einsum, it's much more legible, although it might not look like it at this moment. So what's einsum? I'll just give you a quick look. Basically, this is a function that allows us to perform a lot of operations using the same syntax. And with just a few rules and knowledge of this syntax, you can perform a lot of things very, very concisely. And when you write it, you are able to write your own documentation of what is happening. So we're just naming the dimensions of our matrix and saying how we want those dimensions to move. And einsum einops takes care of the rest. These are sort of the main rules of einsum, but hopefully this has motivated you to look at a tutorial and start learning this very powerful tool. Part of the einops library I want to talk about is rearrange, and we'll be using this quite a lot. And I mention this because it's very useful, and rearrange functionality isn't always supported inside of einsum. So if we look at this example, rearrange does transposing of axes like einsum does. But importantly, the powerful tool here is the parentheses. And the parentheses denote, if it's in the input, say this 24, this denotes the first dimension of 24. And in the output, I'm going to want to split that. So AB is 24. And all I have to do is specify one of these, A or B, and it will infer the other. So I've said I want to split AB here. and I want to see it in the output split out like this. Similarly, for DE, I've specified E. It infers that D is 3. And then when it comes time to create our output, they've been split, and we've even been able to recombine. So we can both reshape dimensions out, and we can collapse them. So in the output, I wanted C and E to be combined and move to the first dimension. So we've compacted a bunch of transposing and reshaping into one kind of flat operation. And this is particularly useful, as we'll see, and we look back at, for example, the einsum of QK. We get to rearrange this very efficiently by just saying, right now I have batch by sequence length by number of heads and head dimension are combined right now. And I want you to split those out and then transpose it such that I have batch and then heads and then sequence length and then dimension. So in a way, you don't really have to decompose it into these functions. It's very easy to just kind of name the dimensions that you have, name what order you'd like them to be in, and write it down. And einsum takes care of the rest. So I've gone ahead and rewritten our multi-head attention with einsum, and I'll put that here. And I've basically just cut out the manual rearranging of tensors and dropped in the einsum version. Okay, so now we're moving on to building the KNN memory. So let's build KNN attention in the exact same way that we built our regular attention. So we'll build it line by line, and we'll check the shape as we go to make sure we're doing everything correctly. And let's start with some fake data. So we know we'll need queries that we'll be getting from here, but they're inside this class. So let's just work with them in memory here. And then we're going to have KV memories that are retrieved. But we don't want to actually compose these things right now. We just want the right shape of what we'll get out. So our memory KV is in the right shape here. And this is what we're retrieving from KNN memory. And then I just have a scale parameter because we will want to scale the attention scores. But for now, we'll just put that as 1. We just want to remember to put it in. First step, we have our queries in this shape. Let's rearrange them. Great. This is what we'll use to search the KNN memory. So we're not actually going to search the KNN memory. That would look something like, KNN search, and then queries, and then top K. But we're not connecting our KNN memory right now. We're just going to use our fake KV. So that would be that. So we're just going to borrow our fake remembered KV values. We want to unbind them, and we'll just do that explicitly with unbind. And this says, in the negative second dimension, I want you to split that. So these are batch by sequence length by 3, that is K by 2. And so we're saying along this dimension, it's the negative second dimension, -1, -2. Split these out. And so I'm splitting them into the K memories and the value memories. Key and value memories, rather. And then we'll rearrange these. Great, we got the right shape. Now we need to prepare for the attention scores. So we want our regular queries and our keys from memory. So we need to rearrange the queries, and I know we've gone back and forth rearranging the queries, but we need them in this shape, and we can optimize later. And now all we have to do is call einsum. So einsum with the queries and the memories. So we have the shape of the queries here, bhtd, and the memories here, bhtkd. And what we want to do is get t by k in the output. And this is okay. You might think it's weird to have the k here, but remember that we have the values, and the values also have a k dimension. And so we'll get rid of the k dimension when we multiply all of this by the values. And then we can multiply this by the scale. It's not really totally necessary right now. Now comes softmax. So this should look very familiar to what we did when we built regular attention. I'm just going through it so we can watch what happens with the k dimension, because that is a new piece. So now we have the attention scores, and we need to multiply by the values. And we can just spell out our dimensions here. And this is in particular where einsum is very useful, because we have these 5, 6-dimensional vectors that we're dealing with, and it's much easier and much more legible to know what's in each one and what is the shape of the output. So we essentially build in the documentation. This is why einsum is so helpful in something like this. And there we have it. That's the memory. QKV, that is the QKV shape that we want. Now, what do we need to do? We have the local multi-head attention and we have the memory multi-head attention. And now we need to combine these. And so in the paper, they had a gating function. And the gating function just looked like this. Let me make some room here. We multiply one of these by the gate and one of these by 1 minus the gate. And the gate is between 0 and 1. So we're basically just weighting these. Now, it's not just one scalar. It's actually a per head scalar. So we need 8 of these gates, and each one will apply to a different head, so that maybe the model decides that one head over another should pay more attention to the remembered attention, and some should pay more attention to the local, or it can balance it basically however it sees fit. These gates will be parameters, so they'll train as the model trains. So we want something like this, but we need this to match our dimension size. So we have 16 by 8 by 512 by 10, and we can't just multiply this by a gate that is just a single 8-dimensional vector. So what size should this be? What we want is a gate that is heads by 1 by 1. And so this will basically apply, no matter what the batch size is, this broadcast correctly. So we'll have the batch size, and that can be whatever it needs to be. And then for each head, it will apply this, and it will broadcast such that everything inside of the attention matrices here will just get multiplied by the gate number. So just to make this very concrete, if our gate was just 0 through 7, and our attention scores were just a bunch of 1s, but we have 2 batches by number of heads. This has to match. We want number of heads. This is number of heads. And 2 by 2 matrices. This is just so we can see what's going on. When we multiply these will broadcast correctly. So our attention scores of 1s appropriately get multiplied by the gates. So that's just kind of a good sanity safety check to make sure that we're doing this correctly. So that's what our gate looks like. We need to remember to wrap this as a parameter, which we did here. So we'll put our gate up here, and then we combine these by adding the memory times the gate and the local times 1 minus gate. You could do it vice versa. And now we have our combined attention. And then we'll just feed that into an output matrix. And we might have defined this earlier, but essentially this is going to get us back into the correct dimension that we wanted. So those are all the steps to perform the memory attention and then recombine it with the local attention and get us the output that we want at that layer. Okay, so we got there. We've built our KNN attention layer, and I've wrapped this all into a class. We don't really need to go through anything here. it's all just incorporating this into an existing multi-head attention class. So I've just added a few things here to take note of. We do need a top K to initialize into our layer. We've added the gate in the initialization, and we have this top K that gets passed down. We also want to, during the forward pass, we need to include the KNN. We need to somehow incorporate the KNN so that the memory layer and the KNN database and index can talk to one another. And I basically just tidied everything up and put it here. We have a combined QKV and out. And that is except for the relative position values, which we can add in very easily when we put everything together. That is a completed KNN attention layer.